Cool. Hi there. I'm Daniel. I'm Randall's son, and I'm a student at Auckland University. And so, as part of my dissertation this year for my honours, I've been working a lot with the proof system COP. And so, so the name comes from the French likes to name their software projects after animals, and coq is French for rooster. So that's where the name comes from. So in part of that, one of my main interests is this idea of proving the correctness of programs. So I'm just going to dive right in. I'm just going to go through a couple of examples, but I'm going to keep it really short because we don't have that much time. So first of all, this is COP code. This is just to give an idea of what it looks like and maybe see some similarities to Haskell syntax. So plus is defined, so we're talking about natural numbers of the form where there's an O and then 1 is SO and 5 is SO. And so this type signature is taking two natural numbers and returning a natural number. So the single colon is like the double colon. And then we've got a match expression. So this is pretty standard how we can define functions. And fixed point just means that it's a recursive function. But the special thing is that the recursive functions must terminate. So it's impossible to say define a function plus of m and m that returns plus of m and m. It simply won't be allowed to be written. And the way it enforces that is by ensuring that one of the arguments is structurally decreasing. So and here the n prime is smaller, so it ensures that we do terminate. But then the interesting thing is that we can also write theorems. And so here we have a theorem. So again, this is within the language. And so this theorem is very trivial, saying that if we add 0 to a number, we still get that same number. And then the proofs involves the reasoning why that is the case. And so just to point out, it uses induction, which is built into the system itself. So that's just to give a vague idea of what COP can do in a normal setting. But I'd like to unpack what it does in relation to program verification. So there's this example that I want to look at, which is the even numbers. So we have a function here on the slide that takes a natural number and returns a boolean. And it should return true if the number is even and false otherwise. This is actually a bit of an awkward definition of a function. Could easily have been 0 gives true, and then then the successor of n gives the negation even of 1 less. But this works too. So 0 is true, 1 is false, and then basically, if we call it with n plus 2, then we get the same value as even of n. So that should be clear, I hope. And so if we look at the type signature, we've got natural to bool. So that's what I want to just highlight here is that this is about the how. So when we write programming, always we're saying how do we do this, right? So we're describing to the computer, writing instructions for how to carry out the function. And then what we'll move on to now is something that generally what are we trying to get the program to do? Is more living in documentation or specification that we write or comments. But in COP, we can write this in the actual language itself. And so here we can define what we want the even number function to do. So this is a definition which is very standard for math. A number is even if it can be written in the form 2 times n or some other number. And the interesting here is this prop type. So in COP, prop is the type for proposition, which is things we can prove. And it's worth noting that this definition here doesn't actually tell us how to tell if a number is even or not computationally. It just tells us the property that should hold. In contrast to the how, which this literally gives us a recipe for computing the answer. And so now we can define kind of the correctness notion, which is in form of a lemma, a theorem, same thing really. And here, so basically we're saying for all natural numbers, that function we defined earlier must return true if and only if that number is even. And the is even is given by the definition we have here. And so this allows us to define what we mean by the function we have written is correct. So for any function, any system, at some point you have to define what does it mean for it to be correct. Yeah, so that's the kind of the what is the key part that we're adding in to the language. So now we can express what we want. So I hope you'd all agree that we think this lemma is true. And so now we're going to try and prove it. Interestingly, it actually turns out to be quite hard, or at least a lot more hard than we would think. In the future, this might be a bit easier by the development of more techniques which automate more parts of this. But I'll just unpack. So we actually, in my attempt to prove it, I ended up needing or finding it useful to write two lemmas. So the first is that our function returns the value of it on n plus 1 is the opposite of its value on n, which is what we'd expect. And so I'll just highlight a couple of things here, which is that I use induction, which is very common for pretty much any data type that's defined using kind of that fixed point recursion type idea. And then you can also consider cases. So over here, I'm going to destruct. That's considering the cases. So very often in programming, in our heads, when we're checking our code, we're thinking through the possible cases. And so here we can unpack that and delve into each one. And in each subcase, you're considering just that and working out whether the proposition holds true there. And so this is kind of the why. So we've got the what, we're trying to do the specification, the how, and then so why it obeys that specification. Reflexivity. Okay, so reflexivity, I'll actually show you briefly. So here's an example. So this is the IDE. So as you're going through a proof, what you're trying to prove appears on the top right, and it changes as you do commands which kind of manipulate the proof state. So for example, over here, the next command is reflexivity, and what it does is when it gets to, so here we're trying to prove 0 equals 0 plus 0, and so it executes this, which is simplify, and then it's trying to prove 0 equals 0, and whenever you're trying to prove 0 equals 0, then reflexivity is the tactic which resolves that. So you're done proving, and then it moves on to the next goal. Yeah, so reflexivity resolves goals where A equals A. Yeah, so feel free to ask me any questions. Yeah, so that's reflexivity and the first lemma. So then I'm not going to go into this at all, but I just found it helpful to have this second lemma. I'm sure there's easy ways to prove this, but that is what it looks like. And then here's the actual lemma we were trying to prove, which was that the function returns true if and only if the number is even. And you'll note that I used the two lemmas that I mentioned before as part of this. Interestingly, also back earlier here, this is a lemma from kind of the standard library. So you use lemmas that you've from before and from the standard library a lot as you're proving more things. And so this goes through that proof and then proves that it is in fact the case that the function returns true if and only if the number is even. And so then we're confident of the fact that our function even b is doing exactly what we expected it to. And so I just wanted to digress slightly to this different way of writing a notation, which is quite interesting, which kind of combines the what and the how, because we have our function and we have its specification, and this kind of brings them together. So this highlights, I guess, a number of things, but one of them is the richness of the types in Coq. So this is the type signature for a slightly differently written function. So this is the same even b, and it takes a natural number and it returns a boolean such that that boolean is true if and only if the number is even. And so this captures the specification exactly in the type of the whole. Yeah. And then here we can write the same function as before. We can define it. This is an alternative way of doing definitions. And the proof is similar to before.
Is that slide there part of the definition of that one?
Yes.
Written up.
Yes. Yeah. Yeah. So in and here if we so here there's the definition, and then it asks me, so even b prime is not defined until I've finished the proof. And so it uses these obligations, and so only once you reach the last obligation does it say, you'll note over here, only now does it say even b prime is defined. Yeah. So that's, I just put it into 2 slides because it's too big.
When construct starts to do something in the proof field, it's strong. Do you correctly with the code section?
Yeah, good question. Interestingly, so I'm sure many of you are familiar with Quick Check. So there's been I've just recently heard about, so there's a version of that called Quick Check. And I've seen it being demonstrated to basically do similar functionality to Quick Check, and that could be used to do that. But it's not a built-in feature to Cock itself. What will end up happening generally is what does actually happen is if you're trying to prove something that's false, you tend to kind of reach a state in the proof where you realize what you've done wrong because you're kind of trying to prove this thing and it's not working. And you're like, so you kind of can see where the counterexample is from where you are in your attempt to prove it. So that does happen as well. Yeah. All right, so that's the main thing I wanted to go through. The last thing I just wanted to briefly mention was the ability to extract to different languages. So there's the possibility to extract, sorry, jumping around a bit. So for example, you can extract to Haskell, probably the most mainstream. You can also extract to OCaml, and just go like that. And then on the right here, we can see the generated Haskell code. So the Haskell code is only going to be the functions, not the proofs. But at least, if you use it carefully, then you can, and you trust the translation, you can trust the function you've generated almost as much as you could trust them directly from having proved stuff about them in Coq.
Can I just ask, what's the Haskell compiler or transpiler in there?
I don't know, to be honest. I'm sorry, I don't know that one. I have to look it up. I think the theory is at least that it would be small. It's code, so you would have to look at the code of that kind of exporter and see. Great question. Yeah, the thing to bear in mind is that you can't just blindly trust these proofs in theory. What you're trusting is the very small subset, like a very small bit of code that is the kind of the core Coq logic, and the kind of similar to Haskell prelude, like if the Haskell negation was wrong, or like neg function was wrong, like that would be problematic for code across the board. And similarly in Coq, if the kind of Coq init library was wrong, then they'd be problematic. They intentionally try to keep that library and the related kind of very core code small enough that I'm quoting here even, that a determined reader can read and hopefully understand. So that's the idea, to keep that small, and then when you build stuff on it, it doesn't, even if it's huge, it only relies upon the accuracy of that smaller section. Cool, so lastly, I would just like to mention, if you're interested in learning more about Coq and how to use it and how to prove stuff, there's a really, really awesome textbook called Software Foundation. And just recently split off into 2 textbooks, but it's really cool. It's actually quite fun, like proving stuff. Yeah, it's like interactive, so it's quite fun. And then I did want to briefly mention kind of where is it at, what real world links to industry and how's this going. So there's a project called ValVM, which is a project to verify the LLVM. There's a project called Concept, which is has produced a verified C compiler. And then there's related things like Spark ADA, which is being used more on the imperative side. So this is all functional programming, although, yeah, that's mainly functional programming, but it can be used to reason about other things. But Spark is directly for developing imperative software and verifying it. So you have preconditions and postconditions of functions. And then there's other techniques like model checking as well. And then lastly, I just want to finish with mentioning DeepSpec. So this is a project that started recently. It's a collaboration in the States. And yeah, so you'll see LLVM there is part of this, and their overall goal is to, over the next number of years, kind of head in the direction of fully verified systems as a whole. Yeah, so this is kind of where things are getting. You see there's quick check that I mentioned before. Yeah, so that's just a very brief overview of an aspect of program verification code. So, if there's any questions? Yeah?
Bearing in mind I'm not familiar with Pop itself, looking at the implementation and comparing it to the proof, it looks like the proofs are a lot more complex than the implementation. So, where I suspect what would happen with when you've got developers under pressure working on things is when something doesn't quite right, they'll cheat on the implementation to get it to work. Cheat on the proof to get it to work, because they don't quite understand why. Because I'll have more confidence in reading the implementation side of it. Well, that looks right, so therefore there's a problem in the proof of it. I'll tweak that, so yes, then the compiler's happy, right, I can move on. I think looking from what I'm saying now, it makes it look quite hard to spot that effectively your testing side is correct, and that actually it's dealing with a complex implementation. The validation looks like it's going to be a lot even harder to read. Does that match up with your experience of it?
Yeah, kind of. I think it's a good point. Like the proofs often are hard to read, but at the same time, in one sense, they don't need to always be readable. If I go back to this function, so if I've defined the function and I've defined the specification, then if I can be confident of those two things, which these two are the easiest parts, right? Function and specification are the easiest. The proof is the harder part. And once you define the function, or really once you define the specification, then as soon as you have a function, the proof could be ridiculously unreadable. But if it comes through as QED at the end and is provable through the system, then it's true that it satisfies the specification. So if people...
So could you cheat on the proof?
No, yeah. So basically you can't cheat on the proof at all. It's impossible. If you do, like, for example, if you do, like, over here, if I go over proof and I don't finish the proof, I can type, like, admitted, but then you'll see it highlighted as yellow and it says it's declared, it's not proven. So, yeah. The system's designed so that you can't kind of cheat once you're in the proof without making it very, very, very clear.
That's just like
Yeah, yeah. Although it's a bit more like if like for example you can go like A and not A admitted, and then you could prove anything. So it's like and then in theory anything like you can even prove anything of any type. Right? Then you could prove a natural numbers and string, all sorts of like,
Nonsense.
yeah. So like it explodes a lot more if you admit something that's false. Yeah.
I have a question about the proofs. I couldn't follow them too far, but it looked like the destruct concept there. Is that because you define a natural numbers in a set of cases?
Mm-hmm.
So the destruct is just playing apart those separate cases. Is that right? So effectively, the compiler is stepping through the function when it's compiled to check whether this proof is true or not, right? Or at least it's having to destructure the pattern.
Yeah.
Can you write functions that don't have cases, or more? It is very there's no sort of imperative side to it.
Yeah. So there's no imperative side. Although, yeah, I'm not an expert on it, but you can define imperative like things in Pollock, but not directly. No.
Yeah. So it relies on being able to step-by-step structure
Yeah. Yeah. So I mean, you can define a function like let's give an example. Boolean. If you have negation and you can say or equals not A and not B. Full stop. Like so, you can define functions normally like that, but yeah, not